Hello मेरे प्यारे बच्चों. Welcome back. I know your exams are just around the corner and you're all studying so hard. I've been getting so many requests for this one chapter, Thermodynamics. So today, we're going to tackle it together. We'll make it super simple, I promise, and get you ready to score full marks. Chalo, let's get started.
So when you hear the word thermodynamics, does your head start to feel a little shaky? A bit like this? I know. For so many students, it just means tension. You think of all those formulas, the different laws, those confusing graphs, and it just feels like, so much pressure.
But listen to me, there is absolutely no need to worry. We are going to make this chapter completely tension-free. I promise you, by the time we're done here, you'll see how simple it all is. We'll break it down into easy, bite-sized pieces that you can remember in the exam hall, no problem. You'll walk in there with full confidence.
Okay, so what on earth is this big, scary word thermodynamics? Honestly, it's really simple. It's all about just three things: heat, energy, and work. That's it. Think of an old steam train, you know? It burns coal to create heat. That heat turns water into steam, which has energy, and that energy does the work of moving the entire train. See? It's just the story of how these three are related. Simple.
All right, let's jump into the laws. We're going to start with the Zeroth Law. Yeah, I know, it sounds a bit strange, doesn't it? Zeroth? Well, funny story, they actually came up with the first and second laws first, but then they realized there was an even more basic idea they forgot, so they had to call it the Zeroth Law. And this law is super important. It's the whole reason we can even use a thermometer.
Okay, don't let the textbook definition scare you. It sounds all complicated, but the idea is, well, it's simple. You see that phrase, thermal equilibrium? It's just a fancy-pants way of saying that two things are at the exact same temperature. That's it. No heat is moving between them. They're basically just chilling, literally. And this diagram from your book shows it perfectly. Look here. We have system A, and it's in equilibrium with C, okay? And then we have system B, and it's also in equilibrium with C. So what does that mean? It means A and B must be in equilibrium with each other. It just makes sense, right? Here's an even easier way to remember it. I call it the friendship rule. Imagine Arjun is friends with Priya, and Simran is also friends with Priya. So because they have a common friend, Priya, we can say that Arjun and Simran are connected, right? They're friends in a way. It's the same thing here. A and B are Arjun and Simran. C is their common friend, Priya, which is basically our thermometer. And being friends just means being at the same temperature. Easy peasy. Okay, now before we jump to the first law, we need to clear up something super important that confuses a lot of students. Think of it like this. A system, say the gas inside the cylinder, has internal energy. It's like the money you have in your bank account. It's yours. But heat and work, they're different. They are not something the system has. They are like money being transferred. A system can receive heat or do work. It's energy in transit, on the move. You don't have a transfer, you make a transfer. See the difference? It's a really important one.
All right, let's talk about the first law of thermodynamics. And the best way to think about this one is as a simple energy budget. You know, just like how you manage your pocket money. It's all about where the energy goes.
And here it is, the golden formula. Delta Q equals delta U plus delta W. Now what does that mean? It's simple. The heat you give to a system, that's your delta Q, can only be used for two things. Part of it can be used to increase its own internal energy, the delta U, and the rest can be used to do some work, the delta W. That's it. The energy has to go somewhere, and these are the only two options. This picture here shows it perfectly. See the flame at the bottom? That's giving heat to the gas, our delta Q. Now what does the gas do with this heat? Well, two things. One, its own internal energy goes up, delta U, so the little molecules inside start zipping around faster. And two, it does work, delta W, by pushing that piston upwards. So simple. The energy you put in is equal to the energy used. Nothing is lost.
Okay, time for a quick question. Let's test this out. Imagine you give a system 100 joules of heat. That's your delta Q. And you find out that its internal energy increased by 70 joules. That's delta U. So my question to you is, how much work did the system do? Come on, you know this. It's just simple subtraction. 100 minus 70 is 30. 30 joules of work. See? You already understand the first law perfectly.
Okay, so we know how energy moves. But in your exams, they love to ask about the different ways a change can happen. I like to think of them as the four flavors of thermodynamic processes. Let's go through them super quickly. Bacho, pay attention. This slide is gold. Seriously, pause and take a screenshot of this right now. This is your revision cheat sheet. We have our 4 flavors. Isothermal, iso means same, thermal means temperature, so constant temperature. Adiabatic, that's when there's zero heat exchange. Isochoric, constant volume. And isobaric, you guessed it, constant pressure. And look at how the first law formula gets simpler for each one. This table will save you so much time.
And this is another pet question for the examiners. They'll show you a PV graph like this one and ask you to identify the curves, but I have a super simple trick for you. Just remember, the adiabatic curve is always steeper than the isothermal curve. Look at it. The one that drops down faster, the steeper one, that's adiabatic. Just remember that.
Okay, moving on to the second law. This one is really interesting. If the first law says you can't win, you can't create energy out of thin air, then the second law says you can't even break even. It's the law that tells us which way things happen in nature. It explains why your hot cup of chai will always cool down, but a cold cup of chai will never ever magically heat itself up.
Now here's the official statement, the Kelvin-Planck statement. Again, don't worry about the big words. All it's really saying is this: you can never, ever build a 100% efficient engine. It's impossible. No matter what you do, some of the heat energy you put in will always be wasted and lost to the surroundings. You can't convert all of it into useful work. It's basically nature's way of saying there's no such thing as a free lunch.
So if a 100% perfect engine is impossible, what's the next best thing? What's the best that we could ever possibly hope to achieve? Well, the theoretical answer to that is something called the Carnot engine. Think of it as the most perfect, most ideal engine that could ever exist. It sets the speed limit for efficiency. No real engine can ever be better than it. And that's because it's a completely ideal, reversible cycle with no wastage at all.
And the formula for its efficiency is so beautifully simple. Look at this. Efficiency, that 8s symbol, is just 1 minus the temperature of the cold part divided by the temperature of the hot part. So what's the most important thing to remember here for your exam? If you want to make an engine more efficient, you need to make the difference between the hot and cold temperatures as big as possible. The bigger the temperature gap, the better the efficiency.
Okay, Bacho, we're almost at the finish line. Let's do a super quick, rapid-fire revision of the most important points for your exam. Ready? Let's go!
These are the formulas you absolutely must remember. First up, the first law. Delta Q equals delta U plus delta W, your energy budget. Next, for an adiabatic process, PV to the power of gamma is constant. For work done in an isothermal process, W equals mu RT ln of V2 over V1. And finally, the king of all efficiency formulas, the Carnot efficiency. Eta equals 1 minus T2 over T1. Memorize these.
And to finish, I want to leave you with a big idea to think about. If even the most perfect, ideal Carnot engine can't be 100% efficient, that means every time energy changes form, anywhere in the universe, some of it gets lost as waste. This waste energy increases the total disorder, or what scientists call entropy, of the universe. So, if the universe is constantly getting more and more disordered, what does that say about its ultimate fate? A little food for thought. All the very best for your exams, my dear Butchholm. You are going to be fantastic, I know it.